Hey, this is Mr. Peterson. This screencast is about a couple of big ideas about cellular energy. So, energy types that cells use energy for, and then a couple of different kinds of energy. So, a little bit of review. So, we've got energy types. First of all, there's kinetic and potential. Now, in the past, in physical science, for example, kinetic energy we saw as energy of motion. Well, cells are moving for sure, but then we have some kinetic energy that's because of heat, or kinetic energy because of sound, or kinetic energy because of electricity. Then we also have stored energy. So kinetic energy and potential energy. Potential energy is probably not energy of position, more like chemical energy that's being stored in chemistry, chemicals that are happening inside of cells. And then we have a couple of different ways that cells are using energy through metabolism, those chemical reactions that drive movement, or chemical reactions that are making or breaking things. And we call those catabolic or anabolic reactions. So catabolic, we break things down, and anabolic, we build things up. So back to the energy. First of all, we have to think about that first law of thermodynamics, and all that states, it's a law, so it's really important, is that energy is neither created or destroyed. It's only transformed. So it never goes away, it just turns into something else. So sound energy gets turned into mechanical energy. Mechanical energy gets turned into electrical energy. Chemical energy gets turned into kinetic energy. It's always just transformed. It's never destroyed. Now in living things, we deal with something else. We deal with entropy, which is the movement of a system towards disorder. And the same thing is true of energy. So energy starts out as usable in chemical bonds, like in glucose or lipids, fats and oils, or in proteins, and eventually that energy is degraded. It kind of falls apart. So we start with lots of usable energy. We call that free energy to do work, but eventually that energy just kind of falls apart as it's used and transformed and used and transformed till eventually it's just lost as heat. So living things are not very efficient at keeping energy around. It's always just lost as heat. And that's due to the second law of thermodynamics, which says that eventually all energy is going to be unusable for living things. So we take in, you had some frosted cardboard nodules for breakfast, and eventually it's going to be lost as heat. So if you put your hands close together, you can feel that heat. That's unusable energy. It keeps you warm. It helps your chemical reactions happen, but you can't do any work with it. So then if we kind of change gears and talk about metabolism, and we've got a couple of different types of reactions that are related to energy. So we kind of put the idea of energy and metabolism together. And the first types of reactions are exergonic. They give off energy. So if we look at the graph down below, you can see the ball starts up high. It's got high potential energy, and at the end, it has a lower potential energy. That energy was used to do something. Probably a catabolic reaction is like that. It gives off energy, so it loses energy. It loses energy of position, in this case with that marble or that ball or whatever it is, and we've got a loss of energy. So the reactants have more energy than the products. But then we have endergonic reactions, and they store energy. So anabolic reactions tend to be like that. They go from a place of a lot of entropy, a lot of crazy chaos, into organization. And that's a way to store energy, and we call those endergonic reactions. So the products have more energy than the reactants. So we'll get into a couple of examples here in just a second. One of the things that helps cells do that is a coupling mechanism, a coupling molecule. Coupling, which means it helps put those exergonic and endergonic ideas together. That's the molecule of ATP, adenosine triphosphate. And so we have those three phosphate groups. The negative charge on those is repelling that third phosphate is always trying to go somewhere. It's a tenuous kind of bond between those, and we use this molecule to couple exergonic and endergonic reactions. So exergonic reactions are catabolic, so cellular respiration, where we're taking in, again, your frosted cardboard nodules, whatever it is you had for breakfast, lunch, or dinner, whatever, and we're going to use that energy to drive some other reactions. So that energy is going to be usable. The coupler is ATP. So adenosine diphosphate, ADP, plus PI, so that's an inorganic phosphate, which means it's not part of an organic molecule that has carbon in it. And we're going to use that energy to take those two things, ADP and P, the phosphate, and put them together to make ATP. So the energy has now been stored. We coupled that energy, that exergonic reaction was used to do some anabolism, so that's actually an endergonic reaction. But then we're going to release that energy again to drive some endergonic reactions, which could be building things, so building other molecules, or moving the cell, so the cell itself moving, or things in the cell moving that are going to require energy, so they're going to absorb energy. They're going to require some energy. Those are endergonic reactions. And so ATP is the coupler between those. So big ideas. We have catabolic and anabolic reactions. We have kinetic and potential energy. And then ATP is the coupler. So the big idea is about cellular energy. Hope that helps.